Now we look at 4-point charges arranged in a square. And let's put like charges in opposite corners. So we'll make this positive, we'll make this positive, we'll make this negative, we'll make this negative. And as we've done before, so we can communicate clearly, we'll label all the charges. And I'll start with this as Q1, Q2, Q3, and Q4. And it's a square, so the distances are all equal, and which is the side of the square. Actually, the distances aren't all equal. I'll get to that in a minute. And we'll make the signs of the charges vary, but we'll make the magnitudes the same. And as we've done in the past, we'll just call it Q to stand for charges of the same magnitude. What I didn't do last time is label these. I'll call this a negative Q because it's negative. Positive Q. This is equal to negative some quantity Q. Since we're using the same symbol, it means that they all have the same magnitude, whatever that is. And now we could look at any one of these charges, but let's look at Q1. So now there are 3 other charges. There's 4 charges altogether. Q1 sits there. There were 3 other point charges, Q2, Q3, and Q4, acting on it. So when if we want to know the total force on Q1, we have to consider 3 vectors. So let's show those 3 vectors. We'll go in numerical order. 2 is acting on 1. It's an attractive force. It's down. And you can see that Q4, same distance, same magnitude, is going to be an attractive force of the same length. So if I label these, this is F 2 on 1. This one here is F 4 on 1, a little crowded. And then the third force from Q3 on Q1 is a repulsive force. So if this were drawn correctly, it would be a square. The force would be along the diagonal of the square. And because the distance, oops, what's happening here? Because the distance is, I should make the vector smaller, or I'm not drawing well. Let's erase that. This vector is going to be smaller. Why is it smaller? Because the distance from Q3 to Q1 is bigger than the distance from Q4 to Q1, or Q2 to Q1. What is that distance? We should mark it on our figure. It's this distance here. It's the diagonal of the square of side S. So if you do the trig, you'll find out that this is the square root of 2 S in length. In other words, instead of S, it's 1.414 S approximately. exactly the square root of 2s. And that vector that I just drew is f of 3 on 1. So now we want to add those three vectors. So we have the sum of the forces, in this case on 1, is going to be the sum of three vectors. F21 plus F31 plus F41. Okay, this gets a little complicated. I'm going to run out of space, but I can move to another slide to finish this if I want to. So F21, let's look at that. We should be able to do this by now. We've done a lot of easier examples. F21 is at a distance s. So F21 is going to be k. All the charges have a magnitude of q. So q1 times q2 is q squared. The distance is s. That's squared. And the direction in the case of F21 is in the negative j hat direction. Now, I'm going to not have enough room for the F41, but you can see F41 is going to be the same magnitude, but in the positive I hat direction. The F31, let's just sketch this out. Look, has an x component here, which is in the negative I hat direction, and a y component here, getting a little crowded, but you can see that y component pointing straight up in the positive j hat direction. Because this is a square and all the angles are 45 degrees, the components are going to be the cosine and sine of 45 degrees, which is the same. It's the square root of 2 over 2. So if I were to write this in, let's see if I can squeeze this in, we would have k q squared over, notice the distance is square root of 2s squared, so when we square that it becomes 2s squared. We have to multiply that by the cosine or sine of 45 degrees. That's the square root of 2 over 2. And then for the x component of that, it's going to be negative I hat.